This is part of the BocaPhysics series on electromagnetism. In today's lecture, I'm going to discuss Maxwell's equations and the displacement current. We'll begin with what we call the pre-Maxwell equations. First equation, of course, is Gauss's law. The divergence of the electric field is equal to charge density divided by the permittivity of free space. Second equation is Faraday's law. The curl of the electric field is equal to minus the time derivative of the magnetic field. And third equation has no name. The divergence of the magnetic field is equal to 0, and that's a reflection of the fact that no magnetic monopole has ever been observed. The fourth and final equation is Ampere's law. Curl of the magnetic field is equal to the permeability of free space times the volume current density. Now, I want to make sure that these equations are consistent with one another. So let's take a look at Faraday's law. I'm going to take the divergence of both sides. Well, that's clearly equal to 0 because the divergence of the curl of any vector always is 0, no matter what vector we're talking about. The right-hand side really boils down to taking the divergence of the magnetic field, and that is 0, so we're consistent. So far, so good. Let's take a look at Ampere's law now. The left-hand side clearly vanishes when I take the divergence. Again, divergence of the curl of any vector is always equal to 0. The right-hand side, however, presents a problem. That's equal to 0, but only in certain cases, only for steady currents. In fact, more generally, the divergence of the volume current density satisfies this expression. The divergence of the volume current density plus the time rate of change of the charge density, or the time derivative of the charge density is equal to 0. This is a continuity equation. So here's the problem with Ampere's law. It holds fine in magnetostatics. However, once we start considering time-varying fields, non-quasi-static situations, we've got a problem. A few lectures ago, we discussed electromotive force, and we talked about Kirchhoff's loop rules, and really the focus of that discussion, or lecture rather, was that there is a bridge between circuit theory and that of electric fields, and that connection is not often made clear. One of the examples that I worked through was on an RC circuit. Okay, so there's our battery, there's our resistor, and there's our oversized capacitor. Now, when I was talking about Kirchhoff's loop rules, I said that it's not immediately apparent that you can use Kirchhoff's loop rules to solve this problem. Why? Because the conduction current in this case is clearly not continuous. At the time I said, well, there's a little bit of a quick fix that we can do as far as circuit theory goes. We don't have to delve into heavily the theory of electric fields, but said, okay, we got a conduction current, then we've got a displacement current, and I flushed that out. I am now going to discuss what the displacement current is. So let's go back to the continuity equation, okay? If I substitute in for the volume charge density, the divergence of the electric field, I get this expression. This, basically this boils down to the divergence of the volume current density plus the time derivative of the permittivity of free space times the electric field is equal to 0. So this suggests a fix. I'm going to add an additional term to Ampere's law. And now I've fixed the consistency problem. So now when I take the divergence to both sides, the left-hand side will clearly be 0, and the right-hand side will as well. This new term is called the displacement current. And in fact, if I go back to just plain old Ampere's law, if I were to take an Amperian loop and apply Ampere's law, so that means that the line integral of the magnetic field around a closed path is equal to mu naught times the amount of current enclosed. Okay. Now, if I assume that the surface over which I'm integrating just lies in the plane of the loop, then there's just a flat surface, then there's no problem. However, if I were to distort this surface such that it's balloon-shaped now, and such that the balloon actually goes in between the plates, then you've got a glaring inconsistency there. You wind up with the surface taken, then the amount of current enclosed, conduction current, is equal to 0. So by including the displacement current now, we've taken care of that problem. So it's now the case, even though the enclosed current is equal to 0, well, we're going to have another term as well, that's equal to mu naught epsilon naught derivative time derivative of the electric field and integrated with the surface. Okay? So this is Ampere's law by itself. With this addition of the displacement current, I'm going to rechristen this the Ampere-Maxwell equation. So this begs a couple of questions. We're calling this the displacement current. So is it a real current? Or true current, maybe is a better way of saying that. The answer is absolutely not. And the reason why is that there's no transport of charge. Well, we are calling it a current, so if it's a current, does it give rise to a magnetic field? That's what we studied a great deal in magnetostatics. You had current carrying wires that gave rise to magnetic fields, and we also looked at the magnetic fields due to magnetic materials. So does a displacement current really depends on your point of view. And another question you might be asking yourself, well, you're calling it the displacement current. Is it like the displacement vector? Basically, this term harkens back to an era when it was assumed that there was an ether that filled space. Of course, with that concept was thoroughly debunked in the early part of the 20th century, but the name remains. Notice how I've written these two expressions. It appears that we're treating the time derivative of the magnetic field as a source, and it appears that we're treating the time derivative of the electric field as a source. So you've no doubt heard these two ways of explaining both Faraday's or describing Faraday's law and Ampere Maxwell law, and that is to say that changing magnetic field induces an electric field. And likewise, a changing electric field induces the magnetic field. Some folks have an issue with these two statements because it implies a causality between changing magnetic field and the electric field. And another interesting aspect of the displacement current is actually hypothesized by James Clerk Maxwell, which is what we call the Ampere Maxwell equation. And these are actually now Maxwell's equations. So he hypothesized the existence of this term before there was any experimental evidence for that. That's in contrast to Faraday's law, for which there was ample experimental evidence some 30 years before. And the reason why this is much harder to observe is because this takes place at much higher frequencies, or occurs at much higher frequencies than this expression over here. Okay, so even to this day, there's been wrangling about how this displacement current should be how it should be interpreted. Well, if we look at Maxwell's equations here as I've written them, basically Maxwell viewed the displacement current as electromagnetically equivalent to the conduction current. And James Clerk Maxwell treated the displacement current on an equal footing. Okay, be very careful here not to call this a source term. Okay, And this is also not a source term. But he did treat them as electromagnetically equivalent. And at the risk of getting too far ahead of ourselves here, he worked in what's called the Coulomb gauge. We'll be talking about gauges probably a couple of months from now. And anyway, what the Coulomb gauge owes to the fact that you have freedom to choose the gauge in which you work. In other words, Coulomb gauge, we choose the divergence of the magnetic vector potential to equal 0. Okay? Now, there's an issue here if you think about it for a minute. It appears that we're saying that if there's a change in the charge density, the current density, then instantaneously somebody on, flying around Mars would detect those changes. Okay, so there's no retardation apparent in here. The fact that we've chosen the Coulomb gauge obscures any concept of retardation. So basically, we'll just say there's no retardation from this point of view. There's another point of view due to Lorentz. And there is retardation in that case. This is a Lorentz gauge. In that case, you're going to choose the magnetic divergence of the magnetic vector potential equal to minus mu naught epsilon naught time derivative of the potential. Okay, so there's retardation, Lorentz gauge, and let's see, I need a little bit more room over here. Okay, so retardation, but no displacement current. And really, another point that I want to make here as well, ultimately, it is the charges and the currents that give rise to the fields. So we really should write Faraday's law and Ampere Maxwell equation like this. All I've done is I've pulled the field terms over to the left-hand side, and consequently only the true sources will be left on the right-hand side. So in a sense, the Lorentz gauge is more fundamental in that you are looking at the fields solely as a function of the currents and the charges rather than having these cross terms. Viewing them sort of, I guess the way a lot of people view them, as almost a source, and we really should not, because they're not sources. These are coupling terms. I think that's a much better way of looking at it between these equations. Couples the electric field to the magnetic field. For calculation purposes, let's convert this over to an integral form. So we write this as a line integral of the magnetic field around a closed path is equal to mu naught equal to mu naught times the surface integral of the volume current density plus epsilon naught times time derivative of the electric field. So again, this is a displacement term, and it does appear that we're treating it as source. Writing it this way is perfectly fine for calculational purposes, but do be aware that it really only is the charges and the currents that are the sources. One way that makes it really crystal clear about the dependence that electric field and magnetic fields have on the currents and the charges is to use Yefymenko's equations. This is electric fields equal to 1/4 pi over 4 pi epsilon naught. Okay, Yefymenko's equations. And it's kind of amazing to think that these equations were only published for the first time, apparently back in the 1960s, by Oleg Yefymenko. And you don't need to copy it down, you don't need to know this yet, because we won't be getting into it until at least for a couple of months. The reason why I'm showing it to you now is to show you that this framework of expressing electric and magnetic fields is consistent with charges and currents that give rise to the field. You see there's no displacement term in the expression for the magnetic field. So I will read it off, you don't need to copy it. By the way, all charge densities and all currents are evaluated at a retarded time. Where the retarded time is t subscript r, t is equal to t minus the magnitude of the separation vector over c. So we've got the electric field is equal to 1/4 pi epsilon naught. The first term is just your, in the event that there is no change with respect to time, is just going to be collapsed in Coulomb terms. So that's just charge density times separation vector over magnitude as separation vector cubed. Now we've got the time varying parts. So this is the time derivative of the volume charge density, separation vector over c, magnitude of separation vector squared. Third term in this expression, minus time derivative of the current density over c squared, magnitude of separation vector. Now magnetic field only has two terms, mu naught over 4 pi. This first term, in the event that you don't have time varying fields, just collapses to the plain old Biot-Savart law that we were using back in magnetostatics. Volume current density crossed into the separation vector over magnitude of separation vector cubed, plus the time derivative of the volume current density crossed into the separation vector over c times magnitude of separation vector squared. So these are not particularly useful if you're evaluating electric and magnetic fields, because they get terribly, terribly ugly, terribly, terribly complicated. but the reason why I'm showing them to you now is so you can see explicitly there's no displacement term apparent in here. It just goes back to the sources. So in a sense, I would say the Lorentz gauge is more fundamental than the Coulomb gauge, because you've got retardation involved, and ultimately it is the charges and currents that give rise to the fields. So why are we even bothered with Maxwell's equations? Well, they're a whole lot easier to work with, if you can use that term, with regards to anything electromagnetism. And also, as I said, these cross terms provide the coupling between the equations, and that's how we can derive the electromagnetic wave equations. Okay? Let's apply Ampere Maxwell equation to this expression. We're going to use this one here. Remember, we're not thinking about this as a source. We're just merely using this for the computation. Okay. So if we take the flat surface here, what you'll find is that first term just gets I, right? Because this current pierces the surface, convection current. The second term contributes nothing. Electric field is 0 there. Now between the plates, if we assume that the radius is much, much larger than the width, and despite how I've drawn this, it's a reasonable approximation to write the electric field as the surface charge density divided by the permittivity of free space. And now that's equal to Q over A epsilon naught. And I'll take the derivative of the electric field, because that is what I'm interested in. And I'm also going to multiply by epsilon naught, because that is my displacement current. That's just equal to whatever A times the derivative of Q with respect to time, and that's just equal to the current. If I integrate this term, over the surface of this balloon, if you will, then I'm just going to wind up with I for the contribution from the displacement current. And then you'd have 0 plus mu naught I in that case. Again, you'd have 0 in between the plates because the conduction current vanishes there. So here we are treating the displacement current as electromagnetically equivalent to the conduction current. Okay? So let's go back to my question. Does the displacement current give rise to a magnetic field? Well, again, from a fundamental viewpoint, it's ultimately the charges and the currents, okay? Maxwell's equations are, however, much easier to work with than getting into retardation. So with that being said, I want to figure out what's the magnetic field between the plates. So we'll construct our Amperian loop to lie between the plates. And we'll say that it has radius s. So there for the left-hand side, we've got 2 pi s times b. Now we have to consider the contribution from the displacement current. And at some, let's say, some arbitrary point, we've got mu naught times I over pi r squared. That's the area of the plates. And times dA, when we're integrating over the surface area of this loop. And I should make clear too that we're assuming that the current just spreads out on the plates in an even fashion. And that will be in a circumferential direction. So I'll make sure to lose track of any anything down here. No, it does not appear so. Okay, so this is really, if you want to think about a first order calculation here, because we are making a lot of assumptions about it. So maybe there's your answer. Okay. So in a sense, we're treating it as the displacement current is electromagnetically equivalent to a conduction current. Now I want to modify Maxwell's equations, so they're easier to handle in materials. We talked about polarized materials and also magnetic materials. So as you recall, the bound volume charge density is equal to minus the divergence of the polarization. Also, the bound current density is equal to the curl of the magnetization. And also, bound surface charge density is equal to the dot product of the polarization and the normal to the surface. So these are hold for static fields, so what happens if we have time varying fields? Well, let's consider a little chunk of material here. And we'll see the material is polarized. And therefore there'll be bound surface charge density on the right-hand side and negative of that on the left-hand side. What happens when the polarization changes in time? Well, what you're going to see is that the charges are going to move a little bit. So you're going to have a current flow. And di, a little bit of current, is equal to the time derivative of the surface charge density times dA. And what's that equal to? Well, that's just equal to the polarization times dA. And therefore, we have a polarization current density that is equal to the derivative of polarization with respect to time. Now, I'm going to make sure this satisfies continuity equations, so therefore, if we take the divergence of both sides, indeed it does. The divergence of the polarization current density plus the derivative of the bound charge with respect to time is going to be equal to 0. So it does satisfy the continuity equation. So there is a change if we are dealing with time-varying fields. Now, what if the magnetization changes in time? Well, that won't contribute to any extra terms. Certainly magnetization changes, but beyond that, we won't see any other terms in our Maxwell's equations. Okay, so total charge is equal to the free charge, and I should write that right, the free charge and bound charge, and that is equal to PF minus divergence of the polarization. Now for the current density, we have the free current, normal conduction current, and then we also have bound current, that's due to the magnetization, and then we have the polarization current as well. I'm going to plug these back into my Maxwell's equations. Plug that into Gauss's law and make use of the fact that the displacement vector is equal to permittivity times the electric field plus the polarization, I can rewrite this expression as the divergence of the displacement vector is equal to the free charge density. So that's our first equation. And let's see, divergence B equals 0 doesn't change. And also Faraday's law doesn't change. However, the Ampere-Maxwell equation will change. So let's rewrite that as curl B minus mu naught. Actually, I'm going to move this term over to the right-hand side. I make use of the fact that H field is equal to B over mu naught minus magnetization. I can rewrite this as curl of H is equal to the free current density plus the time derivative of the displacement. Okay? So those are Maxwell's equations for materials. And again, as before, these are fine. It's just that now, because we are dealing with materials, polarized materials, magnetized materials, it's convenient to separate out the free sources and free charge and the free current, and rewrite these expressions and such. Let me erase this on the left-hand side. Okay. And these need to be supplemented by constitutive expressions. So, or linear isotropic medium, which is the only kinds of problems we consider in this course. This is equal to and remember the Chi's susceptibility. This is the electric susceptibility, and this is the magnetic susceptibility. So these are your equations in materials. I'm going to rewrite these equations in integral form. Faraday's law, I'm going to pull this term over to the right-hand side. Okay, first equation, we're taking the surface integral of over the normal component of the displacement over a closed surface, and that's equal to the total amount of free charge enclosed by that surface. Over here we have the magnetic flux through a closed surface is equal to 0, and of course that's a reflection of the fact that there have been no magnetic monopoles ever observed. Third equation, Faraday's law. We take the line integral of the electric field around a closed path, and that's equal to minus the derivative with respect to time of the magnetic flux through a surface that spans that closed path. Okay, over here we have the line integral of the H field around a closed path, and that's equal to the amount of free current enclosed by that, and this is the derivative with respect to time of the displacement, surface integral of the displacement through the surface that spans this path. Okay. Now I want to sketch out here, get our interface between two different substances. And I'm going to draw a little Gaussian pillbox. I'm going to make this pillbox very, very thin. In that case, the size will contribute nothing, and I just need to worry about the displacement in the electric field above and likewise below. So when I apply this to my Gaussian pillbox, I'll wind up with there being a normal discontinuity in the normal component of the displacement vector, and the discontinuity is equal to the free surface charge density. Applying the same kind of reasoning to the magnetic field, I see that's equal to 0. The normal component of the magnetic field across this interface is going to be 0. Now, in order to investigate these last two equations to come up with boundary conditions, I'm going to construct an Amperian loop. And once again, I'm going to make it very, very narrow. If I make it very, very narrow, the left and the right-hand sides will contribute nothing, and I'll be left with, on the left-hand side, E greater than tangential component dot L, where L is the length of the Amperian loop. Minus the time derivative of the magnetic flux through that loop. Now, if I make it very, very narrow, the flux is just going to go to 0. And therefore, you'll find that the parallel component of the electric field, or tangential component of the electric field, is equal to 0 across this interface between two different kinds of media. Now, what about the H field? You can use the same Amperian loop, and this time around, the volume current density won't contribute anything. However, you will have a contribution from the surface current density. Now we'll assume KF is flowing into the screen, or into the board rather. And these are your boundary conditions. Now, it's convenient to express these only in the terms of electric and magnetic fields, and again, because we are dealing with linear homogeneous isotropic media, I can rewrite this boundary condition as permittivity of the material above the interface times the normal component of the electric field above the interface minus the permittivity below the interface times the electric field, normal component of the electric field below the interface is equal to the free surface charge density. And of course, the normal component of the magnetic field is just written the same way. And likewise, the tangential component of the electric field is the same. And then getting to the last equation, we have the the tangential or parallel component of the magnetic field above the interface divided by the permeability above minus magnetic field, tangential component of the magnetic field below the interface over the permeability below it is equal to the cross product of the free surface current density and the normal. So those are your boundary conditions, and we will be making ample use of these, especially coming up in electromagnetic waves when we don't have sources here. So basically in that case that would be 0 and that would be 0 as well.